All right, audio check. Audio check. Bradley, can you hear me? Sophia, can you hear me? Checking to see. Okay, good. Video check. Can you see my goatee? Okay, awesome. Let's get this party started. So, I'm redoing a video. Hopefully, this works. I'm sorry for all the people who had technical troubles. I had to log out and log back in. And I'm going to post this video up and then we'll see if you guys can figure this stuff out. Bradley, Sophia, make sure you're very talkative with me. I want you folks answering every single question of mine. That way I know whether or not you can hear me or not. Okay? And then I forgot to start. What's going on, chemistry students? Let's get this party started. So what I basically did is I said, all right, imagine, all right, PV equals nRT. I just solved for V. That's not that hard. You just take that P, throw it down there. And then what I said was, use your calculators and tell me, what is the volume of an ideal gas? Because this is the equation for ideal gases. What's the volume of an ideal gas if I had 1 mole of something at 0 degrees Celsius and 1 atmosphere of pressure? It's pretty easy. It's you just plug in those numbers. By the way, you don't put in 0 degrees. You put in 273.15 Kelvin, because you need your temperature in Kelvin. And you just plug it in and you end up getting 22.42 liters. This is the volume that all ideal gases will be at if you have it at a very standard temperature and pressure. By standard temperature and pressure, I mean about 0 degrees Celsius and pressure of 1 atmosphere. We cool? All right. So the volume of so that's why I have the volume at STP, which is standard temperature and pressure, is 22.42 liters. It's about the size of a giant beach ball. A giant beach ball, which we have a lot of in Hawaii because we're surrounded by the beach, is about the size of 22.42 liters. So that's how much gas there is in the stuff. Mastin, since you're late, I'm just kind of re-explaining this. We haven't gotten very far because we had a lot of tech issues, and we're not going to go for very, very long. But essentially, PV equals nRT, solve for V, we good? And then I plugged in a few numbers. I said, okay, well, N is, let's pretend N is 1 mole, and T is 273.15, and P is 1, and R is, our standard R. What is V? So this is a common volume because 1 mole of gas, 1 atmosphere pressure, and 273.15 Kelvin, that's a pretty standard measurement, 0 degrees Celsius. Are we cool with that? And I just plugged those numbers into here and I solved that, and apparently it's 22.42. Okay. Yeah, well, we haven't done anything yet, really. That's all we went over. So if it's all right with you, I'm just going to erase that. And then here's what I'm going to do. I'm going to read the problem to you. A sample of nitrogen gas has a volume of 1.75 liters. This is the volume of nitrogen gas. How many moles of N2 is present? Okay. So this is my volume. Oh, I'm sorry. It's 1.75 liters, not V, it's liters. All right. Well, this is pretty straightforward. I told you that 1.75 liters of gas, if I wanted to convert that to moles, I know that 1 mole of gas at standard temperature and pressure is 22.42 liters. I guess I forgot to tell you that this gas is at STP. So if it's at STP, I can use this conversion factor. We cool? And then this would give me my moles of gas, or in this case, the gas we're talking about is nitrogen gas, N2. So you just take 1.75 divided by 22.42, and you end up getting 0.0781 moles. Hard? Not hard? What's your thoughts? Good, bad, ugly? Easy. Okay, good. All right. I'm going to erase. Example number 2. Now we're getting into stoichiometry. And here's the thing about it, Maston, is before you came, I told them, hey, we're doing gas stoichiometry. And Bradley's like, no, not gas stoichiometry. It makes me feel like I'm in prison inside of a big glass cage, just like Mr. Balda is right now, writing on top of glass. All right, anyway, let's do it. Same reaction over there. Okay, fine. So we have quicklime. Quicklime, the equation is calcium oxide. Calcium oxide is produced by the thermal decomposition of calcium carbonate. So calcium carbonate, CaCO3. And what it happens is it decomposes from calcium carbonate, which is a solid, into quicklime, CaO, and carbon dioxide. No, dioxide, gas. Are we cool? So here's our equation. Oh, and I talked to the... Oh, okay, Bradley, I'd like to know what your anesthesiologist says. Brent says. All right, but are we cool with this? Calcium carbonate decomposes to calcium oxide and calcium dioxide. Is my equation balanced? Sure. A 1, 1, and a 1. All right, so now the question is, calculate the volume of CO2 produced if 152 grams of calcium carbonate were reacted. So I have 152 grams of this stuff, and I want to figure out how much volume of that stuff I have. Does that make sense? Okay. So, let me draw you the picture of what's going on. I'm going to start off with calcium carbonate. Okay? The problem is I have it in grams of calcium carbonate. And in order to play the stoichiometry game, I'm going to need to put it into moles of calcium carbonate to start. Is that fair? And Bradley, I like what you're asking for. We're looking for volume of CO2. So I'm going to use the stoichiometry game to go from moles of calcium carbonate to moles of CO2. And that's where this balance equation is going to come in. But I'm going to need to convert from moles over here once I'm finished to go to my volume over here. And I have this extra step of, I didn't give you the answer I didn't give you the starting stuff in moles. So you got to convert grams to moles. Now converting grams to moles, come on, you know what to do. What do you do for grams to moles? That is easy. You Google it. Okay, fine. You Google it, and what it will tell you? It will tell you the molar mass. Molar mass. Right? You take calcium on the periodic table, you add carbon, you add 3 oxygens, and you end up getting 100.09 grams per mole. Any questions on how I got that number? No, this should be easy, right? The molar mass, not hard. Okay, all right. And then once we play our game in the middle, we can convert from moles to volume using this STP step that we did, and that was just the previous example that you told me was easy. Are we cool? And here's the stoichiometry game. That we play in the middle. So, again, the stoichiometry game must be played with moles. It needs moles going in, and it has moles coming out. What we have to do is we started off with grams of this stuff, so we need to use the molar mass to convert it to moles because we can't start playing the game until we're in moles. When we're done playing this game, we'll end up with our answer in moles, but the problem is we want it in volume. So I need to use this STP thing where I can convert moles to my volume in the end. Are we cool with that? Do you understand the idea of what I'm getting at here? All right, and I'll tell you what the conversion factor, it's actually really easy in this case. If I'm going to end up with moles of calcium carbonate, and I want to multiply that by something to convert that into moles of carbon dioxide, so mole calcium carbonate to mole of carbon dioxide, I can just look here. 1 mole of calcium carbonate gives me 1 mole of carbon dioxide. So a 1 and a 1. That's the game. That's all it is. It was really easy, actually. It's just a parentheses with a 1 on the bottom and 1 on top. That's it. All right. So let's actually do the problem. I start off with 152 grams of CaCO3. I multiply that by a fraction. Then I'm going to take that and I'm going to multiply that by moles of CaCO3, moles of carbon dioxide. Then what I'm going to do, so look, here's the steps that I took. I started off with grams. I used the molar mass to convert into moles of carbon or calcium carbonate. This is the stoichiometry part. This is the game right here. It's just this one step right here. And then I use what I'm going to do is I'm going to say, okay, I have 1 mole of CO2 gas at STP. So it's going to be, so I'm going to say 1 mole is 22.4 liters. So all you do is take 152, divide it by 100, multiply it by 1, divide that by 1, and multiply by 22.4. And you end up getting 34.1 liters of CO2. Bradley asks, where's the 22.4 liters, or 22.4 from? Well, I told you that the gas was at STP. So if the gas is at STP, you can say that 1 mole of gas is equal to 22.4 liters. This step right here, that step right there, was literally the example we did right before, which you said, and I quote, is easy. So what I did was, I did not a hard step, grams to moles, right? You're good at doing grams to moles. The molar mass conversion, that's something you're really good at. Not a hard step, an easy game, and an easy step. So I would say the stoichiometry of gas is not hard. That's the answer, 34.1 liters of CO2. Can I erase this? Okay, all right. Let's try something harder. I'm going to erase. And I don't have a whole lot of time, so I'm basically probably going to stop at stoichiometry. I'm not going to move to partial pressures. I'll see if I can adjust the homework accordingly. But yeah, I think that's it. All right, let's see. A sample of methane gas. Oh, so we got methane. Is at a volume of 2.80 liters at 25 degrees Celsius, and pressure is 1.65 atm. Okay? And it's mixed with a sample of oxygen that has, oxygen, that has a volume of 35 liters at temperature is 31 degrees Celsius, and the pressure is at 1.25 atm. The mixture is then ignited to form carbon dioxide and water. So out comes carbon dioxide, CO2, and H2O. We cool? Calculate the volume of carbon dioxide. So we want to know volume of CO2, question mark, if the mixture in the end is at 125 degrees Celsius and pressure in the end is at 2.5 atmospheres. Oh, darn, this looks tough. Okay. All right. Let's not be wimps about this. Do you guys know what methane is? CH4. How do you know that, Bradley? Did you just look it up just now, or did you know that off the top of your head? Oh, I was just wondering. Okay. All right, so you're saying that methane, CH4, is mixing in with oxygen, and oxygen is O2, right? And it's going to give me CO2 plus H2O. We cool with that? So here's my methane, and that's a gas. And here's my oxygen, that's a gas. And then, actually, all of this is gas. Gas and gas. And then here's my other question is anything at STP here? Is there anything in here that's at STP? Yes? No? No. STP requires that it's 0 degrees Celsius, 1 atmosphere. And I hate to say this, but there is no 0 degrees Celsius, 1 atmosphere. So I'm not going to be using that 22.4 volume trick. All right, I'm just letting you know off the top of my, off the bat. Okay, do me a favor, and I don't have a calculator on me, but can you guys convert 25 degrees Celsius to Kelvin for me? I'm just going to do this real quick, right off the bat. $25 to Kelvin. What is it? 298. Yeah, good. I agree with that. Is it all right with you if I just write this as 298 or 15 Kelvin? 31 degrees Celsius. Can you convert that for me? $31 Celsius. 304. Okay. 304. I'm going to just write that in. 304.15 Kelvin. And then last but not least, 125 Celsius. Can you convert that for me? Oh, that would be 398, right? Yeah, that makes sense. Yeah, okay. All right. And I did that because, I mean, well, I hate doing Celsius. Or I don't, not, it's not that I don't like Celsius, it's I have to do it. I have to do Kelvin, and I'm doing it right off the bat without even starting the problem because I know that that's what I'm going to have to use anyway. So I don't want to have to worry about that conversion. Is that all right with you? Everyone not freaked out about that? I just erased it and put the Kelvin version. Okay, all right, good. Here's my first question: is we have the equation. The equation wasn't that hard to get. It's much easier than precipitation kind of equations. But is it balanced? Let's make sure it's balanced. We have to deal with balanced stuff first. Is it balanced? Yes or no? No, it's not balanced. Okay, I've got 4 H's over here. I only have 2 over here. I'm thinking I'm going to put a 2 out in front here. Sorry, that's hard to see. Let me erase these gases. You know everything is a gas. So I'm putting a 2 out in front here. That gives me 4 O's, doesn't it? So I'm going to need to put a 2 in front of here. Because now the left side has 4 O's, the right side has 4 O's, the left side has 4 H's, the right side has 4 H's, and I've got 1 C on each side. Balanced? We good? Not hard. All right. Now what I'm going to do is, what I want to do is I want to, what am I doing? Oh, okay, I know what I'm doing. I'm going to do this on the side, if that's all right with you. What I need to figure out is, I'll draw the picture for you. I'm going to need to do the stoichiometry game. And in order to do that, I'm going to need to put in moles of the stuff that I started off with. Does that make sense? The stoichiometry game requires that you put in moles to it. And I think that the question is asking the volume. So you got to go from moles to volume of CO2. Now, here's the thing is, I didn't give you the moles of methane, and I didn't give you the moles of oxygen. But I did give you the volume, the pressure, and the temperature. So do you know how to figure out the moles if I gave you the volume, pressure, and temperature? Pervner. There's my moles is equal to, yeah. So N is equal to PV over RT. We cool? So do me a favor. That's not hard. Maston, can you figure out N of methane? Use this volume, this temperature, and this pressure, and also use R is equal to 0.08206. This is not hard. This is actually this is the homework you just finished. And Bradley, could you give me the number of moles of oxygen? Use this as your volume, and this as your temperature, and this as your pressure. No, you require the calculator, really. You just plug it into this equation right here. But that's the pressure and temperature I want you to use. Tell me what you guys get. And Cameron, why don't you jump on Maston's calculation with him? And Sophia, why don't you jump on Bradley's calculation? I'm just doing this on the side. .75. This would be this one. Moles O2. Okay, cool. And then, Maston, did you get it? Oh, 0.08206. 1.88. Okay. 0.188. Is that what you're telling me? Okay. So, let's play this game. All right? Now, I got a question. Was this hard? No, not really hard. No, after you did the gas laws homework, it wasn't hard. So now we have the moles to put in, and we can play the stoichiometry game. Okay? So, what I'm saying here is if you put in 1.88 moles of CH4, I'm starting off with moles. Now I can play the stoichiometry game, and I can say, okay, well, moles of CH4, and I'm going to moles of CO2, because that's what I want to get in the end is CO2. Using the balanced equation, which is right up here, I know that one of these moles of this yields one of those moles of that. Does that make sense to you? Because there's a 1 out in front here and a 1 out in front here. We cool? Do you understand where I got this? Yes? No? Are you guys saying no? I can't tell. I get it. Okay, good. All right. And then what I want to do is I want to convert. Well, first of all, let me see how many moles of CO2 that is. Well, that's pretty easy. It's just 0.818 or 0.188 times 1 divided by 1. That gives you 0.188 moles of CO2. That's pretty easy. Okay. What about the oxygen? Let's try that. If we start off with 1.75 moles of oxygen, and we want to go from moles of O2 to moles of CO2, let's see, the coefficients tell me to put a 2 down here and a 1 over here. So what is 1.75 divided by 2? Like 72.5 or something like that? What is 1.75 times 1 divided by 2? Wait, it's 0.188? Really? No. What is 1.75 divided by 2? Come on, you guys. I don't have a calculator here. What's 1.75 divided by 2? 0.5. I don't know. I'm not good at math in my head. 0.875. All right. All right, here's my question. Which reaction takes place? Which reaction actually takes place? This one or this one? The one with the methane or the oxygen? Which one is my limiting reagent? We're getting into the idea of limiting reaction here. And after I finish this problem, we'll be done. The methane. Yes, exactly, because it's smaller. Here's what I'm saying. With this much methane that you gave me, you can only create 0.188 moles of carbon dioxide. With this much oxygen you gave me, you can create this much moles, 0.875 moles of carbon dioxide. The problem is, where are you going to get the extra methane after you've created 0.188 moles of whatever? Does that make sense? Well, it's saying that after you've created 0.188 moles, you've used up all of your methane, so this reaction is not going to take place. If you had, and this goes back to that s'mores thing, right? If I have a limited number of marshmallows, but I have as many graham crackers as I want, there's only so many s'mores I can make. If I have a limited amount of methane, I can only make this much CO2. If I have this much oxygen, I can make this much CO2. But the problem is, after I make 0.188, I ran out of methane, so the thing is done. Yeah, you don't have enough methane to actually make this much CO2. That's what we're saying. So I'm going to erase this bottom part because this thing, or actually I'll just cross it out. This doesn't happen. Almost, we're done. We're just about done. It's actually really easy at this point. You know the moles of CO2. I'm asking for the volume. And I gave you the temperature and pressure. So in order to figure out the volume, I can just use that. So my volume is this number of moles times R times T, this being the T, and this being the P. And then done. Done. That's it. You guys can go. If you plug in the numbers into there, I think you end up getting 2.47 liters. Humor me and try that out for yourselves. But yeah. That's that problem. It was a really tough problem, but not really that bad. I know it looks crazy, doesn't it? And I'm still trying to convince you that it's not bad, but I mean, think about it. Getting the N wasn't hard. Getting the N wasn't hard. You guys did that and you told me that that was easy. Getting the equation, I literally almost gave it to you. Maybe you would have to look up what methane is. Balancing the equation, not bad. Okay? Then doing this step, was that hard? Like this parentheses, where did it come from? Was that bad? No, not difficult. This came from the equation. You have one methane going in, one CO2 coming out. This also came from the equation. This is the game that we played. This is the stoichiometry right here. Two oxygens going in, one CO2 coming out. Then you just cross out which one's the limiting reaction, and you take that limiting reaction and you plug it back into PV equals nRT, because they asked you the answer. What is the volume? They gave you the pressure right here. They gave you the temperature, and you also know the number of moles. So you know everything you need for this gas. So you just plug in PV equals nRT, solve for V, you have nRT over P, and you plug in N, R, T, and P. And you're done. That's it. Yeah, okay, fine. It takes a while, but it's small steps. Bradley, you can leave. You could leave a long time ago. I apologize for keeping you late. Yes, you're right. It takes a long time. They're easy steps. They're hard. I mean, they're not hard steps. Maybe it's hard to piece them all together. I feel like if you understand this picture right here, it makes things a lot better. You got to play the stoichiometry game. You have to put in moles to do it. You come out with moles, and there's various ways I can ask you to answer. So you need to be able to convert from moles to grams, or moles to liters, or moles to, whatever. Did I cut out? Did I die? Well, good. Class ended. So, sorry. Let me stop the recording.